All right, in this video, we are going to move into section 7.3, which is titled Trigonometric Substitution. So in this video, we are going to talk about a kind of a different variation of U sub. U sub, like I told y'all way on back in a previous video, is a very strong tool. We've used it almost every section since then. But we're going to now look at what happens when maybe U sub is not enough. Is there another technique to help us solve certain integrals, and that's called trig sub. So in some circumstances, our U substitution can be in the form of a trig equation instead. This will particularly be true when it comes to square root problems. So in these next 4 or 5 integrals that we're going to see in this section, inside of your square root is going to be one of the following 3 expressions, either a squared minus x squared, a squared plus x squared, or x squared minus a squared. And what our goal is based on the expression that we have, we are going to do a particular trig substitution along with applying a particular identity that we've already seen from the previous section in order to get rid of the square root and form into a problem that we know how to solve. So let's go through these 3 rules together. If you have the square root of a squared minus x squared, then you will let x equal a times sine of theta, where a is just the square root of your a squared term. And then once you substitute that in, the identity 1 minus sine squared equals cosine squared should show up to allow you to get rid of the square root. If this identity does not show up, you picked the wrong trig substitution. If you have the formula expression a squared plus x squared inside of your radical, then we will use the trig substitution x equals a tangent of theta, and then you will eventually use the identity 1 plus tangent squared theta equals secant squared theta, which will allow you to cancel the square root. And finally, if you have the square root of x squared minus a squared, we will use the trig substitution x equals a secant of theta, which will allow us to use the following identity. Secant squared theta minus 1 equals tangent squared theta, and then that will allow us to get rid of the square root. So once again, this is a technique in order to get rid of square roots where regular U substitution will not work. So we're going to do some problems, and the first 3 problems, we're going to do one of each rule. That way you can kind of see their idea. So example number 1, what is the indefinite integral of this x squared over the square root of 9 minus x squared? Now you'll notice when you look at the square root, U sub will not work here because the power outside of your square root is higher than the power inside. So that's not going to be very helpful. So when we do trig substitution and we look at our square root here, this square root matches the form, the square root of a squared minus x squared, which tells me I need to use the trig sub a sine of theta. Now, since our a squared matches up to 9, that means that when you take the square root of 9, your a value is going to be 3. So for my trig sub, I'm going to do x equals 3 sine of theta, which then I have to convert my dx term. So dx would equal 3 cosine of theta d theta. Because if you change one x into theta, you got to change your dx in terms of something else. Substituting that information in, now here's the difference. Unlike a normal U sub where you only plug it into one particular spot, in trig sub, you have to let every x inside and outside the square root equal your trig substitution. So the x squared on top would be 3 sine of theta all squared divided by the square root of 9 minus 3 sine theta squared times your dx term, which is 3 cosine theta d theta. If we were to expand all those squared terms, you would end up with 9 sine squared theta over the square root of 9 minus 9 sine squared theta times 3 cosine theta d theta. Now remember, your ultimate goal here is that your square root should cancel if you did your trig substitution correct. So inside of the square roots, you're going to have to factor in order to get the identity to show up. Well, I noticed that both of those terms share a 9 in common, so I could factor that out front to make it inside the square root. 9 times 1 minus sine squared theta, and then you're still multiplying by 3 cosine theta d theta. Now, inside the square root, this 1 minus sine squared is the identity that I told y'all earlier should show up. And we can replace that with cosine squared of theta. And now you're able to simplify and get rid of your square root. Because on the top of the fraction, you're going to have 9 sine squared theta. The square root of 9 times cosine squared would be 3 cosine theta, and then you have a 3 cosine theta d theta. And now you can start simplifying. 3 cosine theta over 3 cosine theta cancels, and this gives us the integral. I'm going to go ahead and factor that 9 out front, and that would be 9 times the indefinite integral of sine squared theta d theta. This is the techniques that we covered in the previous video. Since sine is an even power, you will have to use your half angle identity, which is 1/2 times 1 minus the double angle of cosine. The extra 1/2 you have now picked up can be factored out to the front as 9/2. And then I am able to integrate just the parentheses part inside the integral, which would be theta minus sine of 2 theta over 2 when you do your anti-chain rule. And then you pick up a plus c. Now, just like in U sub where you have to go back to the original parameters, that is the same thing in trig sub. We need to get these thetas back into x's. Now, that can only be done is if everything is in terms of a theta or a singular trig function. The issue we have right now is that we cannot have a double angle of sine in our answer in order to go back to x's. So therefore, I'm going to need to use an identity, one that we saw in the last video, and we know that sine of 2 theta is equal to 2 sine theta cosine theta, all divided by 2 with a plus c. What that also allows me to do just very nicely here is that 2 over 2 cancels, and now we have it in the right form. But the question is, what do all of these values equal? Well, if you take your original trig sub, the x equals 3 sine theta, we could solve for the trig function in that problem, and we could say that x over 3 is equal to sine theta. Since we are using Pythagorean identities to do this problem, we can assume that this has to be the definition of sine on a right triangle. And we learned back in trig that sine has a definition of opposite over hypotenuse as far as its ratio goes. You could then use Pythagorean's theorem to find the missing side of your triangle, or a nice shortcut here is that what will always happen in trig sub is the original square root in the problem will always be the missing side, no matter which side it is. So you could verify that by doing Pythagorean's theorem if you wanted to. Now, going back to my problem, if I substitute in what I have, theta can be found by taking the inverse sine of both sides to get theta by itself, because theta can't be found by itself from this triangle. So I could say that theta is the inverse sine of x over 3 minus, then you have to multiply a sine function times a cosine function. So sine, we already know, is x over 3. You can find cosine directly off this triangle by doing adjacent over hypotenuse, which is the square root of 9 minus x squared divided by 3 with a plus c. And then if I distribute that 9/2 to both terms inside the bracket, you should get 9/2 times the inverse sine of x over 3. Well, the 9 on top will cancel both of the 3's on the bottom, so you'll just get a minus 1/2 times x times the square root of 9 minus x squared with a plus c. And that is your final answer doing trig substitution to solve this problem. So there's an example of where a sign substitution can be used to help you find the final answer. All right. Once again, in these longer rules, we don't always give you definite integrals, but I do want to do one because this is one of the easier problems to do. So what is the integral from 0 to 2 of dx over the square root of 4 plus x squared? So when you go to set up your trig substitution here, when you look at your square root term, that has the form the square root of a squared plus x squared, which tells us that we need to do the substitution of x equals a times tangent of theta. So when I set up my trig substitution, since a squared is 4, that means a has to be 2. So I'll let x equal 2 tangent of theta. And then dx would have to be 2 secant squared theta d theta. Now, since this is a definite integral, we are going to have to change our parameters here. So what might be a little bit easier is that if I were to go ahead and get my trig function by itself, so x over 2 equals tangent theta. Because remember, these values are x's, so you're not plugging them in for theta, you're plugging them in for x and solving a trig equation. So starting with 0, if you let x be 0, that means that tangent of theta equals 0. So we're plugging these values right there. The only value where tangent is 0 in your interval from earlier is 0. And then if you plug in 2, that would give you 1. Tangent is 1 at pi over 4. Now you can sub your trig substitution in. The dx term on top is going to be 2 secant squared theta d theta. Actually, what I'll do is I'll put the d theta on the end when I'm done. So divided by the square root of 4 plus, then you've got to take 2, oops, not secant squared, sorry, 2 tangent. I plugged the wrong thing in. 2 tangent theta all squared. And then I'll go ahead and put that d theta from the top out here by itself. I need to clean up what I can. So this is the integral from 0 to pi over 4 of 2 secant squared theta over the square root of 4 plus 4 tangent squared theta d theta. Now remember, that square root should cancel when you're done, so we're going to have to factor again to set up an identity. So this is the integral from 0 to pi over 4 of 2 secant squared theta over the square root. I'm going to factor the 4 out of each term, and that leaves me with a 1 plus tangent squared theta left over. And from the identities that we went over earlier, 1 plus tangent squared can be replaced with secant squared, and now we can apply our square root. So this would be the integral from 0 to pi over 4. On top, you still have a 2 secant squared theta. And then on the bottom, the square root of 4 secant squared would just be 2 secant theta d theta. Well, the 2's cancel, and you can cancel one of the secants off, and we are left with an integral from 0 to pi over 4 of just secant theta d theta. Now, while this is not one of your traditional 6 trig rules, it is one of the rules that I said you had to learn when we did the video on section 7.1. So if you need to go back, if you haven't started learning those yet, you need to know them because they randomly show up. The integral of secant is the natural log of secant theta plus tangent theta, which we are going to evaluate from 0 to pi over 4. When I plug pi over 4 in to get my values, the secant of pi over 4 is going to be root 2. The tangent of pi over 4 is 1. And then minus the natural log, if you plug 0 in, the secant of 0 is 1, plus the tangent of 0 is 0. Now that second natural log that we got, this becomes the natural log of 1, which we have learned in the past is 0. So therefore, your final answer here is just going to be that first term, which is the natural log of root 2 plus 1. And that is the exact value of the definite integral above. And that is how you would approach a tangent substitution with trig sub. All right, so we've done sine and we've done tangent. So let's hit on that last rule and then we'll do a couple of other things after that. Back to indefinite, what is the indefinite integral of dx over x squared minus 1, which is raised to the 3/2 power? Now, the fact that it's raised to the 3/2 does not change our approach here because the 2 on the bottom represents a square root. So we will go about this the exact same way. So first off, we have to identify which trig sub we're going to do. So if you look inside, and I'm going to write square root up here because there is technically a root here. If you have the square root of x squared minus a squared, this tells us that we need to do a secant substitution. And since our a squared is 1, we can also let a equal 1. So therefore, we have one of the easier substitutions we've seen so far. X just needs to be secant theta. But when you take the derivative of that, the derivative of secant is secant theta, tangent theta, d theta. Substituting all that information in, you will get the indefinite integral of secant theta, tangent theta. I'll put the d theta out to the side in just a second. And then inside your parentheses, you will get secant squared theta minus 1 raised to the 3/2 d theta. Just like the previous 2, at least that root, that 2 on the bottom should go away when all is said and done. So let's see what happens here. That is a direct identity that we covered earlier. So on the bottom of your fraction, we can substitute in that secant squared theta minus 1 is going to be tangent squared theta raised to the 3/2 power. And when you raise a squared to the 3/2, the 2's will cancel, and this will leave you just with secant theta, tangent theta, over tangent cube theta, d theta. Now that does simplify. You can cancel one of your tangents off. So this tangent cancels one of those, and we will end up with the indefinite integral of secant theta over tangent squared theta. Now, this is not one of your rules or one of your strategies that we covered, so we're going to have to use some other known identities to get this into something that we know how to integrate, either from a rule we've covered in the past or one of the rules off of our chart. So the first thing I know is that I could flip-flop tangent squared over because there's an understood 1 on top, and I know that 1 over tangent squared would be cotangent squared. So I can rewrite this as the indefinite integral of secant theta times cotangent squared of theta, d theta. All right, not quite there. I know that I can rewrite cotangent squared using a quotient identity So that would be cosine squared of theta divided by sine squared of theta. Now that I have this in terms of sine and cosine, let's also do the same thing for secant. I know that secant is 1 over cosine, so let me also substitute that in. I'm just trying to play around with this so I can get something to cancel. And the first thing I see finally cancels. This cosine on the bottom cancels one of the cosines on top, and we are now left with a cosine theta on top and a sine squared on the bottom. Now that something is canceled, let's see if that now allows us to reduce it back into something that we know how to integrate. So if I were to take the cosine on top and divide it by one of the sines on the bottom, that would be cotangent of theta. And then if I take the understood 1 on top and divide it by the other sine on the bottom, that would be cosecant of theta. That is one of the rules that we should know. The integral of cotangent times cosecant is going to be negative cosecant of theta plus c. But we need to get this back into terms of x for our final answer. So earlier from your original trig sub, we know that x equals secant of theta. So I'm actually going to rewrite that down here at the bottom while I draw my triangle that I need. I could rewrite this that x over 1 equals secant theta. And we should know that the definition of secant on a right triangle is your hypotenuse over your adjacent. So the hypotenuse is going to be x, the adjacent is going to be 1. Now, the missing side is always the original square root. So at the beginning, you had x squared minus 1 to the 3/2. The 3 would not be a part of the original square root. So your missing side is just the square root of x squared minus 1. And that can also be found by doing Pythagorean's theorem. Now I can use that triangle and I can find my value of cosecant off and substitute it in. Well, cosecant has a definition of your hypotenuse divided by the opposite, which would be x over the square root of x squared minus 1. Don't forget the negative when you did the integral, and then don't forget your plus c. And that would be your final result for this problem. So that is how you could do a problem with a secant substitution. You substitute your value, and then you got to do a little bit of manipulation to eventually get to something you know how to integrate. That's always the goal. So the last 3 problems have shown you how the 3 main rules work. But there are times that you may have to do a little bit of pre-work before it sets up into a rule that we've covered. So the last 2 problems in this section are going to demonstrate that idea. So let's look at this first one. I want you to evaluate the integral of the indefinite integral of the square root of x squared plus 2x. This does not look like one of your substitution rules. That's because it's not in the right form. So in order to get this quadratic function into the right form, we're going to have to use a technique from algebra called completing the square. So if you recall from algebra, you can complete the square. So we would bring down the x squared and the 2x. You can take your value of b, which is 2. You will divide it by 2 and square it. So up here at the top, if you take 2 divided by 2 and square that, that is 1 squared, which is 1. So what completing the square says you're allowed to do is you can add 1 and you will subtract 1, because technically you cannot change the value of the original integral. So adding 1 and subtracting 1 keeps everything the same. But now inside of your square root, the first 3 terms should factor into something very nice. So they actually factor into x plus 1 all squared, and then you bring down the minus 1 that you picked up. This now fits the mold of one of your substitutions. It looks like the general form of the square root of x squared minus a squared. Now our x is actually x plus 1 and our a squared is 1. But that doesn't change the fact that you're going to have to do a secant substitution to make this work. Now, instead of doing x equals, you technically have to do x plus 1 as far as your substitution goes. A squared is 1, so therefore a would be 1. So we'll let x plus 1 be secant. And therefore, we could find dx to be secant theta, tangent theta, d theta. Substituting in my new trig sub, we should get an indefinite integral of the square root. That's going to become secant squared theta minus 1 times my dx term, which is secant theta, tangent theta, d theta. Secant squared theta minus 1 is one of the identities that we talked about, so we can rewrite this as the square root of tangent squared theta times secant theta, tangent theta, d theta. Well, the square root of tangent squared here is going to actually end up being secant, and then you're going to end up writing that as secant times secant, which is tangent. All right. Oh, sorry. I said the wrong thing. The square root of tangent squared is tangent, and then tangent times tangent is tangent squared. Sorry, I was looking at the wrong thing and I was paying attention. So you should get secant theta times tangent squared theta, d theta. Now, here is the issue with this problem, is that this is not one of your strategies that we have learned so far. Secant is not even and tangent is not odd. So we can't go along with those strategies. We'll have to do something a little bit different here. So my suggestion would be is change something that we can. We know how to rewrite tangent squared. We just talked about it. I could actually write this as the integral of secant theta times, and I know that tangent squared is equal to secant squared theta minus 1. Then if I distribute the secant to both of those terms, I end up with the integral of secant cubed theta minus secant theta d theta. And now what I can see here is that we have two terms that we have to integrate. This second one is actually a rule we did earlier today. That is one of the rules that I'm asking you to learn from that chart. Secant cubed is not one of those rules. So we're going to have to go over here to the top right, and we're going to do some scratch work to figure out what the integral of secant cubed is, and then we'll come back and attach on the integral of secant. So up here at the top, let's focus on how would you integrate secant cubed theta d theta. That is once again not one of your strategies, so we're not going to go along that way. So instead, I'll go ahead and tell you, the only way to integrate secant cubed is you're going to have to set this up, unfortunately, as an integration by parts formula, which means that in order to do integration by parts, you need to break off something that we know how to integrate in order to set it up. Well, as far as this goes, the easier thing to integrate here is going to be secant squared theta, because we know that the integral of secant squared is tangent, so it'll be easier if we set it up this way. Now, remember back in integration by parts, you eventually want to do the formula uv minus the integral of v du, where we have to pick out which function do we want to be u and which function do we want to be dv. So remember, you let dv be the term that's easier to integrate. So based on what we talked about, that's going to be secant squared, and by default, we're going to let u be secant. You don't need to use Lipit here because they're both trig functions. That's not really helpful. You got to be able to identify which is easier going which direction. Because now I know that du would be secant theta, tangent theta, d theta, take the derivative, and then when you integrate secant squared, that would just be tangent theta. So substituting these values into your integration by parts formula, you would multiply the u and the v, which would give you secant theta times tangent theta minus the integral of v times du. So if you multiply your v and du together, you're going to get secant theta times tangent squared theta d theta, which looks strangely like the same thing we got over here when we were doing our initial trig sub. So we're going to attack this the exact same way, and it's going to bring back another topic we covered in a previous section. So this would be the same thing as secant theta, tangent theta, minus, actually, let's do this. Let me write on the next line. I don't want to cram it on that line. So this would be secant theta, tangent theta, minus the integral, and I'm going to once again substitute for tangent squared, secant squared minus 1. Distributing that secant through will give us secant theta, tangent theta, minus the integral of secant cubed theta minus secant theta d theta. Now, we actually know how to integrate this minus secant theta. So let's go ahead and do that here because we're trying to simplify this the best we can. So this will be secant theta, tangent theta. I don't know how to integrate secant cubed yet, so we'll just leave that alone. And then if I multiply this negative in front of the integral times the negative in front of the secant, it becomes plus. And the integral of secant is one of the rules that we've learned, which is the natural log of the absolute value of secant theta plus tangent theta. Now, if you remember back when we did integration by parts in 7.1, the last problem we did in that section was called a cyclical integration problem. And that's actually what we have here, because this integral that we've come up with came from the original integral secant cubed. So if you end up getting back to what you have, all you have to do is set the answer you found equal to the original integral that we're trying to solve. And then you can solve an algebraic integration problem to solve for the cyclical answer. So if I move this negative secant cubed d theta to the other side, I can say that secant theta, tangent theta, plus the natural log of secant theta plus tangent theta is going to equal 2 times the integral of secant cubed theta d theta. And then to solve for the original integral of secant cubed, I can now divide everything by 2, and I can say that 1/2 secant theta tangent theta plus 1/2 the natural log of secant theta plus tangent theta is equal to the integral of secant cubed theta d theta. But you're not done. That was only one part of the original integral that we have to solve here. So now going back over here in blue, we are now going to substitute in what we know. So the integral of the secant cube part of the original trig sub would be 1/2 secant theta tangent theta plus 1/2 the natural log of secant theta plus tangent theta. Then you have to subtract from this the integral of the secant theta that we left to the side. So if you integrate secant theta, that would be the natural log of secant theta plus tangent theta. And then you pick up a plus c finally. Now, very nicely, your second and your third natural logs actually go together because they are the same thing. So you will have 1/2 secant theta, tangent theta, and then 1/2 minus 1 is a minus 1/2 the natural log of secant theta plus tangent theta plus c. and you are officially done integrating. Unfortunately, you're still not done with this problem. So you have to go all the way back up to the top. Let's see if I can find it, but almost. So the very top here in red, the original trig substitution needs to be used to help you solve and rewrite this integral into terms of x. Your final answer must be in terms of x. So over here on the right, we know that x plus 1 is secant theta. So when I draw my right triangle to make the relationship, remember theta is going to be your angle here. So x plus 1 can actually be rewritten as just x plus 1 over 1 to create that ratio. And secant has a definition of hypotenuse, which is x plus 1, divided by the adjacent, which is 1. And then remember, your missing side is always the original square root in the problem. So way back up here, the original square root is the square root of x squared plus 2x. All right, so now I'm going to go back to my integral, and I'm going to replace the secants and tangents with the values coming from this triangle. So this would be 1/2 times secant of theta, which we already know is x plus 1. Tangent is opposite over adjacent, so that would actually just be the square root of x squared plus 2x minus 1/2 the natural log of secant theta, which is x plus 1, plus your tangent value, which is the square root of x squared plus 2x, and then plus c. None of that simplifies together, so therefore, after all that work, this is your final answer. And you see, when it doesn't fit one of the molds, it can be very difficult throughout the process. So kind of running through what all that was. We had to do a completing the square in order to get it in a form to do trig sub. When we performed our trig sub and simplified, we knew how to integrate one of the terms, and we did not know how to integrate the first one. So I brought the secant cubed up here, and we had to use integration by parts to get all the way down to the bottom of the purple text. And then I substituted, after finding the cyclical integration, I substituted that along with the integral of the secant I left behind in, combined like terms, and then I did my resubstitution to get my answer back in terms of x. And that is your final answer to number 4. So let's look at one more problem for this section that is not initially a trig sub that we are going to convert into a trig substitution. So we have the integral from 0 to pi over 2 of cosine of x over 1 plus sine squared. Now, with trig functions involved, there is not any kind of completing the square or anything like that you have to do. Instead, we need to convert all of these trig functions into just singular letters. And the easiest way to do that here is let's actually begin with a very basic u substitution. Now, I don't want u to be the entire inside of the square root because that's not going to be helpful. Instead, if I want this cosine of x on top to go away, I can just let u be sine, because I know that du is going to be cosine of x dx. Now, since this problem actually begins with a u substitution, you will have to change your parameters. So we're going to let 0 and pi over 2 get plugged in for x to get the new parameters. Sine of 0 is still 0, but sine of pi over 2 is 1. On the bottom of the problem, you get the square root of 1 plus u squared, and then this entire cosine of x dx term is exactly our du term. Now this is the form of a trig substitution, no longer a u substitution problem. So if I set up my trig sub, this fits the same mold as the square root, so I'll do this at the top here, It is the square root of a squared plus x squared, which tells me I need to let x equal a tangent of theta. Now, ours is obviously not x, so we're actually going to use u here. So I'm going to let now u, so my new u is going to equal tangent of theta, because my a squared is 1, so I can just let it be 1 for a. And therefore, du is secant squared theta d theta. I got to change my parameters again. So these parameters are u, so you're going to substitute them in for u to solve for your new parameters. Tangent will be 0 at 0, and tangent will be 1 at pi over 4. Your du is going to be secant squared theta over the square root of 1 plus u squared, which would be tangent squared theta, and then I'll bring that d theta out to the end. 1 plus tangent squared is actually going to be secant squared. So if this becomes secant squared of theta, I can take the square root of that to give me the integral from 0 to pi over 4 of secant squared theta over secant theta d theta, which I can then divide that and get the integral from 0 to pi over 4 of secant theta d theta, which that is one of the rules that you have to do off your chart. So we know that the integral of secant theta is going to equal the natural log of secant theta plus tangent theta, and we are going to evaluate this from 0 to pi over 4. So this is actually the exact same integral that we saw, I believe, where's my notes here? We saw this on the second problem. So if you want to go back in the video and see what I did there, it's going to be the exact same process, but you should end up with an answer of the natural log of root 2 plus 1. And that's just a coincidence. We ended up with the same thing based on the problems I picked out. But either way, that is how you can start off with a u substitution that then becomes a trig substitution in the end. So that ends the video for trig substitution. Good news is that in the next video, we're going to veer away from trig for a little bit, and we're going to learn an idea called partial fractions in the next video.